In this video, I'll be going over integration and the net change theorem. So this is what the change theorem says. If we have a definite integral of some derivative of a function, to evaluate that, we take the original function f evaluated at b minus the original function evaluated at a. Now this looks a lot like the fundamental theorem of calculus, and it is essentially the same thing, but the interpretation is a little bit, we're just going to interpret it slightly differently, I guess. So inside the integral, what we have is a derivative, and what we know about a derivative is that this is a rate of change. Okay, specifically, how is a function changing? So if we take the integral, more specifically, a definite integral of a derivative, what we end up with is the original function. And in this case, the original function is just f. And we're evaluating that at the limits of integration at b and a. So here, this is just the original function. Okay, so if we take an integral of a derivative, we end up with the original function. Okay, so we'd say that the net change of a function is the definite integral of its derivative. So let's look at a couple examples and we'll see how this works. And again, the net change theorem is just one of the many interpretations that we can apply to a definite integral. Okay, we'll start with a basic example. It says, write an integral and evaluate it that expresses the increase in the perimeter, P of S, of a square when its side length increases from 2 to 4 units. So let's look at what this is talking about. So suppose we have a square and its side S here. Okay, so all 4 sides are S. So we can write a function or a table of values here, where S is the side length and P of S is the perimeter. So if the side length is 1, the perimeter, or P of S, of this square is 4, because we have 4 sides. If the side length is 2, we get 8. If it's 3, we get 12, and so on. So it looks like the rule here is going to be, if I have some value S, the perimeter is 4S. And if we think of what the graph looks like of this function, so what we end up with is P of S is equal to 4 times S. So this function, if we were to graph it, is just a line that has a slope of 4. Okay, so what we want to do is we want to find an integral that expresses this relationship when the sides of the square increases from 2 units to 4 units. So suppose this is 2 and this is 4. So one way to think about this is we want to find how much change has occurred when we're from 2 up to 4 units. Okay, and one way we can do this is to find the integral here. And so what the net change theorem is telling us is, well, from a to b of the derivative of some function, d of x, if we integrate that derivative, we end up with f of b minus f of a. So in this instance, we're going to treat p of s as our original function. So if we take the derivative of that function, we just end up with 4. So our integral here is going to be, we're going from 2 to 4 of 4, and I'm going to say that because the variable of integration is s, we're going to say 4 ds here. So when we take the integral, when we find the antiderivative of 4, that's going to be 4s. Again, when we take the antiderivative, or we take the integral of this derivative down here, we should end up with our original function, and then we're going to evaluate that from 2 to 4. So I have 4 times 4 minus 4 times 2, and we end up with 16 minus 8, which is 8. Okay, so this makes perfect sense. Suppose in my table of values, I went down to 4. I would have had 16 here. So what this scenario is saying is what's happening when we increase from 2 to 4. What's happening in here? And we see that we're increasing from 8 to 16. So the net change is 8. Okay, another way of thinking of this is the y value here, when we have 2, the value of the function is 8, up to p of 4 is 16. So we've seen that we've changed this net change here is 8. Now you might be thinking, well, why do we need to create a definite integral of this when we could have just made a table of values or very easily have graphed this to see what the net change is? And that's true for this particular example because it's so straightforward and pretty simple. There's other ways we could have done this, but if we ever end up with a function that is more complex, it might not be as easy to simply make a table or graph, especially if we have the limits of integration are not just between a couple integers away. If we had this between 1 and 100, that might be more complicated. So we'll see what happens when we have more complex functions here. Okay, this example says a motorboat consumes gasoline at a rate of 5 minus t cubed gallons per hour. How much gasoline is used for the time between 0 and 2? So t is in hours here. So we want to know how much gasoline is used. In other words, what's the net change in the amount of gas that has been used by this boat? So we're going to take the integral from 0 to 2 of this function, 5 minus t cubed, and dt. So the integrand here is a rate, so we can interpret that as the derivative of some function. And so when we integrate that derivative, we're going to end up with the original function. So we're going to say 5t minus t to the 4th over 4, and we're going to evaluate that from 0 to 2. And so we're going to have 5 times 2 minus 2 to the 4th over 4. Then we're going to subtract, well, when I input 0, that's just going to be 0 here. So we end up with 10 minus 16 over 4, which is 10 minus 4, so we end up with 6. So that means the motorboat or the boat used 6 gallons over the first 2 hours. And let's consider that same boat and suppose it was out on the water for 10 hours. How much gas was consumed in the 5th hour? So if we're talking about the 5th hour, that is between hours 4 and 5. So suppose it starts at, goes out on the water at 12 noon. The 5th hour would be from 4 o'clock to 5 o'clock. So we'd say 4 to 5 here of that same function. Okay, and then we're going to evaluate this in the same way. So when we say something like this, the 5th hour, right, the first hour is from 0 to 1. The second hour is like this. So this is the 5th hour down here. It's a common mistake to say that the 5th hour would be between 5 and 6 hours, but we need to be careful not to make that mistake. So evaluating this, we're going to say 5t minus t to the 4th over 4, evaluated between 4 and 5. And what does that end up with? Now, this is what happens when you just make up a situation. I ended up with negative 87.25, and that doesn't even make any sense for this scenario because we couldn't use negative gallons of gas. But the whole point of this second example is how we translate the 5th hour into our limits of integration here. So if you're ever to see an actual question that was, thought up in more than 10 seconds, you would get something that would actually give an appropriate value down here. All right, in our last example, it says, given the velocity function v of t equals 3t minus 5 in meters per seconds of a particle in motion from time equals 0 to time equals 3, that's in seconds, find the net displacement and the total distance traveled. So net displacement and total distance. Now we need to differentiate between what these two things mean. What is displacement and what is distance? So let's suppose I start at my house and I go to my school, and then so S for school, and then I go to the park, and then I end up, let's just say I do that. So if we're talking about what the net displacement is, well, suppose I start at my house and I walk to school, and then I walk to the park. Once I'm at the park, the net displacement is going to be whatever this distance is. This is going to be the displacement. Okay, so it's kind of the total change from the initial position to the ending position is net displacement. If we're talking about the total distance traveled, that's going to be whatever this length is plus this length. That's going to be the distance. Okay, so the displacement could be negative. This could be negative, right? If we do everything, if I walk to school and that's in a positive direction, and then I walk back to the park, and that's how we're oriented in the negative direction, my displacement could be negative, but distance will always be positive. So now that we know what distance and displacement mean here, let's go ahead and answer this question. So since we're given a velocity function, v of t, we know that v of t is the derivative of a position function. We could call that s of t, or maybe d of t here. So we know that the derivative of the distance function is going to give us the velocity function. Yeah, that's right. So we're going to say v of t here, and we're going to evaluate this from 0 to 3 dt. Okay, so v of t is the derivative of the distance function. So when we integrate that derivative, we're going to end up with our original distance function. So we're going to say 0 to 3 of 3t minus 5 dt. Applying the power rule, we get 3t squared over 2 minus 5t, evaluated from 0 to 3. So inputting 3, we're going to have 3 times 3 squared over 2 minus 5 times 3. And then we're going to subtract. When we input 0, we just get 0 again, so nothing to subtract. So 3 squared is 9 times 3 is 27. 27 over 2 minus 15. 15 is the same as 30 over 2, so we end up with negative 3 halves. Okay, so that is the displacement here. Okay, so our displacement is negative 3 halves, and that's in meters. So this particle, wherever it started, maybe it moved forward, but then it moved farther in the negative direction, and so its final resting place is kind of behind where it started. So now let's look at the total distance traveled. So for total distance, it's possible that the total distance could equal the displacement if the particle has always been moving in the same direction. However, let's look at what our function is. V of t is equal to 3t minus 5. If we graph this, we get a y-intercept of negative 5, a slope of positive 3. So graph looks like this, that's going to be v of t. Okay, so we're looking between 0 and 3 seconds. So 0 seconds is going to be right here. 3 seconds, when I input 3, I get 9 minus 5 is positive 4. So at 3 seconds, I'm up here at 4. So we need to figure out what value the function is hitting the x-axis, because this area down here is going to be negative, and this area up here will be positive. So when we found the displacement, we figured out, we found this area and this area, and we added these together, and that gave us -3/2. And that just means the area below the x-axis was bigger than the area above the x-axis. But now that we want the total distance, we're going to add up these areas and we're going to make them both positive, and that'll give us the total distance. So the first thing we need to do is figure out, what is this x value? So where is 3t minus 5 equal to 0? So 3t minus 5 is equal to 0 at t equals 5/3. Okay, so what we're going to do is we're going to come up with two separate integrals here. So from 0 to 5/3 of 3t minus 5 dt, that'll give us the lower area. It's going to give us this. And then plus, we're going to say from 5/3 up to this value is 3 of the same function, 3t minus 5 dt. And this integral gives us this area. Okay, so since we want distance here, we need to, we can think of this like we're taking the absolute value of whatever we end up with as that integral, because based on the graph, we know that if we evaluate that definite integral, we're going to end up with a negative value because the area is below the x-axis. But because we're talking about distance, we want to make sure that it's positive at the end. So let's go ahead and evaluate. We end up with 3t squared over 2 minus 5t from 0 to 5/3 plus the same antiderivative, 5/3 to 3. Okay, so doing all the evaluations and simplifying this down, we're down here. I'm at -25/6 minus 3/2. This is plus 25/6. Now what we need to remember is that this first integral corresponds to this negative area, but because we're talking about distance, we want to give that the absolute value at the end. So this will be positive 25/6 minus 3/2 plus 25/6. So that's 50 over 6 minus 9/6 is equal to 41 over 6. So that is the total distance that has traveled by this particle.